The region below is bounded by y equals half x, y equals 3, and x equals 11. So you get this right here. Here's x is 11. This is, change the color here. This is was a half x. And this is y equals 3 right here. Okay, so there's a little region. And now we're going to rotate it two ways. First, we're going to rotate this region around the y-axis, set up an integral for the volume created. Then we're going to rotate it around the x-axis and set up an integral for the volume created there. It's going to be two different three-dimensional shapes depending on how we rotate this thing. So let's start with the first one, y-axis. Going to rotate it about the y-axis. That means I'm going to grab this chunk and rotate it that way about that y-axis. What's that going to look like? Well, here's what it's going to look like. I went out to the Desmos 3D calculator. Here it is. Can you see it over there? Right. Here's the I turned it a little bit. Here's the x-axis. Here's this so you can see the inside, right? So here's the x-axis, here's the y. So it's going to produce that three-dimensional bowl-like shape with the hole in the middle, right? And this, this is going to come up over here, right? You can picture this coming up over here on the other side of the y-axis, right? And these discs like this, well, that's what you're going to get. Okay, here it is from the back, which will make it easier for us to set up their integral because you can see the washer, the back of the washers really clearly. Okay, so let's set it up. How do we do? These are washers. Just look at this. That's a washer, meaning it's a disc with a hole in the middle. So you know how to find the volume of each washer. It is pi big R squared, the outer radius, minus pi little r squared, the inner radius, times the thickness, whether that's dx or dy. Okay, well, we're integrating dy. That thickness is going to be dy. So each washer is going to be pi. Now, what's the bigger radius square? It's a bigger radius. You can tell the bigger radius goes from the middle all the way out there. That is the big radius. That's the outer radius of the washer, right? How far does that go? Looks like I went a little too far here. It goes right there to this point, which is at x equals 11. You can tell. Right? You can even see on the 3D grapher, there's 10, there's 11, one more. We can see it right here. The washers are going to sit like this, getting back to this thing. The washers are going to sit, here's the center of them. There's the outer radius, which is 11, right? They all have the same outer radius, as you can tell on the three-dimensional picture. They all have the same outer radius. So what changes is the inner radius. They all end, see how they smooth out, they all end at the same point. The outer radius is the same. What's different is the inner radius. The inner radius gets bigger as we go out up the y-axis. So the outer radius is 11. That's easy. Minus pi, and now the inner radius. And then we already said the thickness is dy, right? Where their thickness is going in this direction. We're stacking them up, dy. See the little thickness going that way. Okay, anyway, what is the little inner radius? Now, the little inner radius, we can see it right here. That's the little r. And what is that? Well, that's the x value for that equation right there. What's the x value for that equation? Well, we're going to need to multiply both sides by 2 to solve for x. Boom. X is 2y. So the little radius is 2y, isn't it? The x value. So this is 2y squared. The little radius is 2y squared. So we can see it, the little inner radius, the outer radius, and you can see the little inner radius right here if it helps to see it one more time. Little inner radius, And what is it hitting? It's hitting that diagonal line right there. The diagonal line is, what was it? Y equals a half x. Yeah, it's y equals a half x. That line, so the little radius is the x value, right? It goes how far on the x-axis. And so that means the little radius is actually 2y, because when you solve that equation for x, you get 2y. So the little radius is 2y. That is 2y, and the outer radius is 11. All right, so we got our integral. We're going to integrate from, oh, and where are we going to stack them up? We're integrating, you can tell we're stacking up these disks from the bottom, right? This is the bottom of all the disks are like this, aren't they? And so we're going from the bottom, which is 0, or sorry, 3. 3 is the bottom to the top, which is 5.5. That is the top. We're setting those up from 3 to 5.5. So there's our integral from 3 to 5.5. Pi, just factor the pi, 11 squared minus 2y squared dy. That integral will compute the volume of this weird three-dimensional shape. Now, part 2, we're going to take that same region. Now we're going to rotate it the other way. In fact, here it is. Here's the region shown again for us. Let me bring down, what are the equations there? That's y equals a half x. Let me write them again. Line on the top is y equals half x. This one on the right is x equals 11 and y equals 3. So this is 11 right here. Starts at 3. And this is y. Did it start at 3? Yeah. And this right here is also 3. Right, because it said y is 3 there. All right, so there we go. There's a little flat shape, but now we're rotating it about the x-axis like that. And so going the other way. And so we get this. You can see I did a 270 degrees of the rotation right there on the 3D thing, right? This is the x-axis. This is the y-axis. This is the z. As you go into, 3 dimensions, that's the height. All right, so what is the volume of this other different kind of 3D shape? Well, got a bunch of washers again. You know how to find the volume of a washer. Volume of each washer. Then we're just going to sum up the washers. Each washer, pi, capital R squared minus pi, little r squared. Take the big circle, take out the hole in the middle, times the thickness. That'll get you the volume of each washer. Okay, so what's that going to be? What's the big radius? How far out is the big radius? Well, the big radius, you can tell, I'll put it right here. It goes from the middle up to there. There's the big radius. And so what is that? That's going up to that line, y equals a half x. There's the big radius, r. It's going up to that line. So it's the y height. It's the y height. And what does y equal? All the way up to that line, a half x. So what does r equal? A half x squared. So r squared becomes a half x squared minus, and now pi times little r. So what's the little radius? The inner radius. Well, that would be from here to there. There's the little r, the inner radius, and that's from there to there. That's the little r. What is that? That's just up to 3. All the little radiuses are the same. They're 3. Just coming up to 3. So we say, okay, 3 squared. And the thickness, well, we know the thickness is dx. They're thick dx thick in the x direction, aren't they? Dx, and that matches what we get there. And then just integrate that. Now we just need to put an integral in the front of that. So we're going to integrate that from x equal to x equal, because it's a dx integral from x equals what to what? Well, we're going from 3 to 11 on the x-axis, aren't we? So 3 to 11. Oh, wait, no, that's not 3. That's not 3, is it? What is that number? What is our x value? I missed it. That's 6. 6 to 11. 6 to 11 on the x. That's 6 to 11. So 6 to 11 on the x-axis is that the answer they get. 6 to 11, 0.5 half x squared minus, there we go. We get, so two totally different three-dimensional shapes, both starting from the same flat two-dimensional shape, rotated about the y-axis, get this kind of thing. Rotated about the x-axis, get this kind of thing. Different volumes, different integral formulas. There we go.